So I'm here today to talk to you guys about enabling extreme security with the seL4 microkernel. So to get started, you can visit our website, DornerWorks.com, seL/seL4 microkernel. There you can learn a bit about seL4. It'll cover some of the things we'll cover in today, but give you some more information about how to engage with us on seL4, as well as provide links on how to get the source code and start using seL4 today. So one of the main problems we're trying to address here is how do you show security? The question that comes is my solution actually secure? The traditional approach uses detailed design and penetration testing together. So you have these long development cycles that I'm sure you guys are used to of design, develop, penetration testing, design fixes for bugs and vulnerabilities, and then you just continue that cycle over and over again, developing and then testing, developing and testing. Eventually you get to a point where you decide you're happy for release, but often after that, security vulnerabilities and bugs are often still discovered. So this can result in long-term maintenance and providing customers with frequent security patches, and often leaving them still to ask, is this actually secure? So one of the solutions to this is using the seL4 microkernel. And now this is due to the nature of formal methods that was applied to the microkernel. With this proof, you can make some very hefty claims that you can't make with traditional testing methods. So one of the main things that the proof provides is that the binary code of the seL4 microkernel correctly implements the behavior described in its abstract specification and nothing more. So there is a specification written in a high-level functional language called Haskell, and what this specification does is it describes everything the system can do. And so by meeting what the specification does and nothing more, you can get away with things like claiming shall not requirements, because you know strict bounds of what the microkernel can and cannot do. It's also important because it means that some very common bugs simply can't occur. Things like memory leaks, buffer overflows, null pointer dereferences, basically pointer errors in general, arithmetic overflows and exceptions. All those bugs that are pesky and annoying simply can't happen within the microkernel space itself. The other part of the proof is that the specification and the seL4 binary satisfy the classic security properties called integrity and confidentiality. Integrity means that data cannot be changed without permission, and confidentiality means that data cannot be read without permission. So this is very helpful for any solution that requires some form of guaranteed isolation between different parts in the system. So if you have something that's maybe mixed criticality, where you have a high security side and a low security side, and you need them to not communicate with each other in any way, the seL4 microkernel is a great way to do that because of the proof. And so it's really significant for any solution that requires security, and also it's in the same vein helpful for safety properties as well. And like I was saying, there's basically no way you can make these claims without a proof. One important aspect of the proof is what is it actually proven on? So it's only proven for specific platforms and specific configurations of those platforms. So the actual verification has only been done on the i.MX6 SoC Sabre Light board. This platform is an ARM v7 and excuse me, it has a configuration for 32-bit ARM that goes through the entire gambit of the proof. So that means it meets all the properties that I've just previously described. And the way that it's actually verified is because the proof makes certain assumptions about the hardware, certain assumptions about the configuration, and Data61, the developers of seL4, have gone through, done the proof, and they've gotten, and they've verified that all those assumptions are correct. Some other platforms that have some of the proof going is, and by that it's functionally correct. That's a 64-bit configuration for x86, as well as a virtualization configuration on the NVIDIA Tegra K1 TK1 SOM. That platform is an ARM32 still, but with virtualization extensions. And so besides those, it works on quite a few other ARM platforms and x86 platforms. It's also recently been ported to RISC-V, which some members of the DornerWorks team had some hand in some of the patches to get that accomplished. So there's a lot of functionality there. The proof is catching up to some of the other platforms and some of the configurations available on those platforms. But the best way to see what's covered by the proof, the configuration, is to actually go to the L4V Git repository and take a look at that. And we have some pointers for that. Another major benefit for seL4 is that it's an open source platform. If you've been working with any other open source solutions like Linux, you'll likely have an understanding of why that's usually more of a benefit than a bane, like some people might think. But it's usually useful knowledge to get out there that obviously the biggest benefit of open source is that it has no licensing costs, and so it's free to use. seL4 kernel is licensed under GPL v2, so if you have familiarity with Linux, it works exactly like that, but that does have some restrictions in how you handle the source code and deliver it to people. And then the seL4 libraries and tools, everything you need for user space, are mostly licensed under BSD, and that one's a little bit less restrictive. If you want to know more about what other benefits open source software has, things like how it's actually usually less error prone because there are more eyes watching it, things like that, you can check out a blog that we posted previously. So another important piece that we'd like to go over with seL4 is its design. There's some very interesting ways that things are implemented for seL4, basically to facilitate the proof, or that we're essentially informed by the proof. So first off, getting into kernel space versus user space. When you're looking at a typical operating system, instead of a microkernel, you're looking at things like Linux or Windows, and most everything that touches hardware and provides services lives in the kernel itself. When you're using a microkernel, you're trying to minimize that as much as possible. So what the microkernel provides are really just a few pieces. It provides memory management, scheduling, and IPC, inter-partition communication, or inter-process communication. And outside of that, basically everything else is done in the user space. So this leaves the kernel as small as possible, This helps the proof because it's very expensive to do formal methods and to get a proof solved correctly. And so by limiting the amount of actual code base in the microkernel, then you make it more feasible to do a proof. So some of these things that get pushed out to the user space, like what you would expect to be in a kernel, a normal monolithic kernel-based operating system, things like file system support, things like device drivers, serial drivers, Ethernet drivers, things like stacks, any type of server, all that stuff gets kicked out into the user space, leaving your kernel size much, much. Capabilities are probably one of the most interesting aspects of seL4 and are probably one of the biggest pieces that enables proof. So capabilities are basically a mechanism that is used to grant access to specific resources in the system. So for most everything that exists in the system, a capability will exist for it. So your virtual mappings from virtual address to physical addresses, there are capabilities for those. Objects that you use for IPC is that has a capability, as well as interrupt. Each interrupt has its own capability. So you see basically every resource in the system that the kernel knows about has a capability. And so the reason why these form the basis of security in seL4 is that the kernel keeps track of everything in the capability derivation tree, and the capability is required for any operation on a kernel object. So when you invoke a capability, you're making a system call to the kernel with a capability in mind, and then the kernel understands who is supposed to have access to use that capability and what that capability is supposed to be used for. So it can do checking to know things like, is a bad actor thread trying to gain access to a resource that it's not supposed to have access to. So this is how you get those isolation guarantees, by doling out that access. And so untyped memory is essentially the way you can dole out this access. When seL4 boots, after it initializes everything in the system and it kicks off in the user space, it kicks off into a root thread. And this root thread basically has access to everything in the system, including untyped memory. And so what you do with untyped memory is you basically just have a big chunk of all the memory in the system, and you can retype it to memory as other kernel objects. So you use this to build up capabilities for virtual memory spaces, capability spaces, thread control blocks, and any other kernel objects that you might need. Endpoints in IPC. So endpoints, they're basically a very simple way to communicate from one thread to another, or to the microkernel itself. Excuse me. And so basically what it does is it allows very small amounts of data and capabilities to be transferred between two threads. So you can use this to do things like notify, send a notification from one thread to another to let them know that something has occurred, or you can transfer a capability from the root thread to a new thread that you're kicking off to give it some information about something it has access to, things of that nature. So it's invoked with an seL4 kernel system call, and there are multiple different system calls, some of which are blocking and some are non-blocking. So depending on how you want to pass data through. Depends on which one you should use. And it basically requires 2 threads to have the capability to the same endpoint. So you do have to be a little bit careful in your configuration to make sure you're not stepping over that when you're not supposed to be. So you need to be using the system calls correctly. Then for inter-process communications, the IPC, there is a mechanism for thread-to-thread and thread-to-kernel communication. Messages can be sent to either an endpoint or other kernel object. This communication is still controlled by the kernel, so data only goes to where it is configured to go. And this is useful for communication data. But things like very large files should be transferred to other means, such as shared data. And shared data is just set up as shared buffers that are also still configured via retyped memory using from the root thread. So the root thread would have to set up a shared memory buffer, a shared virtual mapping between 2 threads. So that's something where you really need to make sure if you're opening that up that you know that those 2 threads can communicate that way to each other. Kernel API, we've talked about it a little bit, about how the seL4 kernel expects you to make these different system calls into the kernel, and it's fairly similar to what you would expect to do with, say, a Linux kernel where you make syscalls. But the main difference is how you have to provide the capability to make those system calls so that it can act on the right object. But using these APIs is very important. To take advantage of the isolation and security properties offered by seL4, the system designer needs to utilize the API correctly. So that means using those primitives and mechanisms made available by seL4 and developing applications to adhere to seL4 system API calls. If you try to find some way to circumvent these APIs, then you're going to negate the proof and essentially not get any use out of seL4 for what it's really providing, which is that formal guarantee. So architecting a system, when you're writing seL4, when you're writing applications on top of seL4, there are some default libraries provided. There is a simple library that provides a lot of abstraction of all the, it's actually called simple. It isn't actually that simple, but it provides an abstraction of all of the things you need the root thread to do to get the system up and running. But it's still actually fairly complicated because you need to do everything like retype all the memory and set up all the capabilities, start up create a TCP object and set all the right variables for that and do all that. And that it's definitely doable, but it's the more difficult way to build an seL4 system. So the way that's a little bit easier is using CAMPs, which is the componentized architecture for microkernel embedded systems, which is a mouthful that is essentially to say that it is an XML-based configuration. Well, it's similar to XML. It's not actually XML. It's its own configuration file. But you can use that then to set up your system into different components. You can think of those as similar to applications, and you set up what resources you want each component to have. So a component could then have access to hardware registers, it can have access to interrupts, it can have connections to other components. So you do all that in a couple of files, and then that generates some glue code as well as bringing up and hooks into some C files, so then you can start adding in your applications for those components. That's definitely the easier way to go, but we've done both methods where you also just write the root thread yourself. And so we definitely have a lot of experience architecting systems. One such that we've done was porting a free RTOS application to run on to use Campese instead. And so that there were a little complications there when you're porting from another operating system to a microkernel. They'll often have more features that may be missing that your application was already relying on. So one such thing we ran across was needing broadcast IRQs. We needed an IRQ to go to multiple components. And so that wasn't built in already. So we had to build an IRQ server component that would then broadcast that out correctly. So it'll run into little things like that. And it just takes careful planning, careful configuration, and careful implementation. So again, seL4, we think is one of the best routes out right now for anything that has very rigorous security requirements due to its mathematical proof. This can help you stay ahead of costly brand damaging cyber threats. One example we wanted to give was that I was talking about mixed criticality earlier. But what you may want to be able to do then is have a mixed criticality system, and let's say you have packets coming in through the same Ethernet device, and one is you have some packets that are encrypted and some are not. Well, you would want to then set up a system where you have a router application coming in that is looking at the packets and then sending the encrypted ones out to a more secure application, and the plain text ones can go everywhere they need to in the system. And so then decrypted secret data only shows up in the specific applications where you expect them to. Some upcoming events. There is an SAE training seminar that is in Troy, Michigan. It's a 2-day seminar on March 7th and 8th. And that is something that DornerWorks will be giving. And this will be obviously longer. It's 2 days training. So it'll be about getting to know seL4, getting much deeper into the APIs, getting deeper into the associated proof and all the software components. We'll also be doing hands-on workshops, so you'll actually learn how to build up applications, how to run on a platform. We'll be going through an HTTP server application that we wrote that will help kind of show that separation of using Ethernet and showing a real-world type application. So, and some of the main goals are for people to be able to determine if seL4 is a good choice for your security solution, know how to develop and build basic seL4 applications, describe what the formal proof implies about seL4, and be able to identify capability-based systems. Be on the lookout for future DornerWorks webinars. Currently, they're to be announced, but we expect to have some in the future that are more specialized. So to keep it going, there are a few avenues for communication currently. First off, there is a LinkedIn group that we have a link to right here. Then there's also the seL4 mailing list, so you can subscribe to that and see what is going on with people that are developing with seL4. There's a couple other platforms coming up soon that they're testing out and just kind of getting content on. So there's a discourse group that should be available soon, as well as a Jira where people can put in issues and we'll be able to do RFCs, so the community request for comment on features or whatever, or like any major changes that are coming out. So those are the goals for that. Thank you very much for listening. We will start diving into some of the questions. I'll probably start with some of the ones that we received when people registered. So first off, how can seL4 improve security for ROS2 architectures? Like most things, you need to understand what you're trying to use seL4 for. And a lot of what that is for how do you use the isolation guarantees. So something like ROS that's running on top of Linux currently, you could either split apart some of that functionality into different Linux virtual machines if you're running seL4 and in VNN mode, or you could try to split some of it out of Linux and run in its own guaranteed application space on top of seL4. So those, I think, are probably the most obvious first choices of how you would use that. So what effort do you estimate for developing a device driver? Obviously, it depends a lot on what the driver is for, but the general steps are that you currently have to make certain platforms modifications to the kernel. It needs to understand about the memory ranges and interrupts about those devices if it doesn't already. Then you need to write a driver component which would live in the util-libs, which is the OS agnostic layer, and then you would need to write into the seL4 platform libs. Some of them exist already where they have an abstraction layer that hooks into seL4. If it doesn't exist already, then you would have to write that as well. And then if you want to be able to run on CANPs, you would have to write some supported CANPs templates and components in some situations. So it definitely ranges a lot. I don't have any hard numbers right now, but if anyone wants to further continue this discussion, we can definitely generate some numbers from some other projects that we've done. So another question was, how much effort on average is it to learn and become proficient at seL4 to harden a small system component? So that really depends on the component, and I would say exactly what you mean by harden. So if it's a big piece, if it relies on system resources, the more system resources it relies on, the harder it's going to be, as well as how are you trying to separate this? Are you using VMN mode, and you're just trying to take something that used to live in a kernel and make it into a small piece? That would probably be one of the more realistic ways to go about it. Another opportunity is another way you could do it is by re-implementing everything just in seL4. I'd say that's definitely the harder way to go about it for now. There's kind of some features lacking in the ecosystem to support that. But I would say it's probably more effort than you would expect. And again, like the previous question, something that we could probably get harder numbers on if you want to engage further. What kind of future research work is the group on seL4 looking for? That depends on the people who are the different groups that are working on it. So some of the current goals right now for Data61 is to get their mixed criticality system scheduler integrated into, to get it verified and integrated into the mainline release of seL4. So that will provide more real-time scheduling as well as time isolation guarantees. So that's kind of a side channel right now that's in the assumptions is that timing isolation isn't fully guaranteed, but once they're able to get this verified, then that'll be a nice step. So currently, right now, that's something that you could ask on the mailing list to get more information directly from Data61 or anyone else in the community who may be on the mailing list. Discourse will be a great place for that. I'm also hoping through the Center of Excellence that we'll be able to have a community roadmap up. So at any given time, you'll be able to see what types of features people are looking for. So real quick, as some people have to drop off, they're asking if who to contact. Yeah, you can contact me by email. There's also Greg Wild listed there. So for my email, it's robert.vanvossen at DornerWorks.com. So. So next question, which microcontroller architectures will have seL4 board support packages available to provide basic software? So one of the requirements of seL4 is that it needs an MMU to meet the requirements of its formal guarantees. And so anything without an MMU will likely never be supported. But currently, you have ARM v7s and later, you have most x86 platforms, and now as RISC-V is maturing, you have RISC-V as an option now. Those are currently the platforms that are supported, but anything with an MMU seems possible. And then for actual like device support, that is going to vary much more. So some of the main devices we work with are Xilinx ZUS Plus, as well as NXP with NX8. So we've been working to expand the device support on those, but it's generally dependent on what customer needs are. Next question, are there any plans to implement a formally verified HTTPS ecosystem on seL4 campus? So I know there's definitely interest. I don't know how many people are pursuing it. I do know someone is working on a verified Ethernet stack. So I know it's being pursued a little bit, but it's not something DornerWorks is currently pursuing. But it is an interesting idea. You may, I don't remember who asked this, but you may want to reach out to Kestrel, because they're the ones working on the network stack. We're kind of hoping they'll be a member of the CAU as well. Okay. Another question was, what access to the FPGA would you have when deploying seL4 on a ZCU102? So by default, you don't really have any access to the FPGA. But you can, based on your configuration of the FPGA and when you bring about, when you know what your actual memory and IRQ configurations are, you can then treat those basically like they're real devices, and then add them to your kernel configuration, like we were talking about earlier, where you have to make modifications to the kernel, and then just add it in as a new device. So really, it's just that the kernel needs to understand that the kernel needs to understand what all the devices are in the system. So something like an FPGA, where it can be configured based on your bit stream, you just need to make modifications to the kernel so it understands what the devices are, and then they can be treated like normal. So I would say the one other thing I want to mention is that for needing modifications to the kernel, I know there's interest from both us and Data61 that would like to add device tree support into the kernel, so that when you have modifications like that, like platform modifications, you can just pass in a device tree instead of needing to make changes every time. But this is another thing that we have experience with. We've actually done that with a DARPA project where we used a Zinc MDSoC, the ZUS Plus, sorry, and using that, we've gotten some experience doing that ourselves. So if you want to start an seL4 project, we have a quick start package available. That's something you can buy from us, where we'll go out and we'll do some training for you, and we'll get seL4 running on a platform from a list of available ones, and then kind of help you get your project quickly launched. Jason Lee just sent a message. He's one of our cohorts in COE. He's from II, and so he's just mentioning that we're crafting a technical roadmap together, and he listed an email address where you can send suggestions. Thank you, Jason. Okay, some other questions have come up during the presentation. So one question is, what are the functional or security variations between the 64-bit and 32-bit configuration of i.MX6? So the 32-bit is verified. The i.MX6 is actually an ARM-v7 chip, so it doesn't have a 64-bit version. I think there's definitely interest in the community to getting a 64-bit version of ARM verified. So I don't know where it's at on anyone's roadmap, but I know it's a piece of interest. The next question, are security guarantees provided by seL4 only valid for static systems? The security guarantees hold for any system for the kernel. So the way you build it is basically as a static system. So I would say in most ways that you would define static or dynamic, that is the case. You will build a static system, and that is what the proof applies to. But the proof only really applies to the kernel anyway. So and the kernel's not going to change once it's up and running. It's more about how do you get your isolation guarantees, and if you're dynamically changing your system, you need to do it in a way that you're making sure you're not opening up avenues for communication across different different applications that you may not have access. And then there was a question about if capabilities were similar to SE-Linux access control. They're fairly different. So with SE-Linux, you're trying to set up mandatory access control of certain system resources. I guess they actually are pretty similar. But POSIX capability, SE-Linux uses POSIX capabilities, which does not implement actual capabilities. POSIX capability is not associated with an object. So it's kind of like a similar goal, but a different way to implement them is really how I would say it. And it's really capabilities are in the deep down level of it, where with SEL-Linux, you're kind of just bootstrapping it on afterwards. So it is similar in goals, but I would say you get stronger guarantees using seL4 versus SE-Linux. And I think that covers all of our questions.
Thank you very much, Robbie, for the great presentation today. We hope everyone got what they were looking for out of this. Of course, we've got a couple email addresses that we've given you in the chats and in the slides. Again, we'll be saving this presentation to YouTube, and I will email everyone who attended today a link so you can watch it and see the questions answered. Again, thank you very much for attending. We look forward to communicating with you in the future with our upcoming webinars, and we wish you all success in your development. Happy coding. Take care.